Today we'll discuss pericyclic reactions, and these reactions are categorized into three different categories. First is electrocyclic reactions, second is cycloaddition, the third one is sigmatropic reactions. So we'll start with electrocyclic reactions first. Electrocyclic reactions, there is movement of double bonds. So as you can see, this double bond between 3 and 4 moves to this position. So a single bond is formed between first carbon and fourth carbon, and the double bond between 1 and 2 moves to third and second position. Another example is conversion of 1,3,5 hexadiene into cyclohexadiene. So again the double bonds move to the adjacent positions, and this double bond forms a sigma bond, a single bond between carbon 1 and carbon 6. So if you observe, overall one pi bond is broken and one new sigma bond is formed in electrocyclic reactions. Now let us understand the mechanism of electrocyclic reactions. So now we'll discuss mechanism of electrocyclic reactions. Before that, we should know how do we draw molecular orbitals, because these orbitals are required when we discuss this particular concept of mechanism of electrocyclic reactions. Now let's take a simplest example of ethene, the simplest alkene. In case of ethene, we can draw the molecular orbitals by combining two atomic orbitals, two p orbitals. So for each carbon, I have taken one p orbital. So if you can see a shaded and unshaded region, the shaded region of p orbital says is that region where the probability of finding an electron is maximum. So if we make molecular orbitals, there can be two different orientations. In first case, both the shaded regions are on same side, and this molecular orbital is stable molecular orbital, and we call it as bonding orbital. On the other hand, there is anti-bonding molecular orbital where the shaded regions are on opposite sides. So if now we have to fill these molecular orbitals, there are two pi electrons. So these two pi electrons will be filled in the most stable lowest energy molecular orbital, which is this molecular orbital, right? And the anti-bonding molecular orbital will remain empty. Now let's take an example of 1,3-butadiene. In this case, there are 4 pi electrons, and the total number of molecular orbitals formed are also 4. Let's see how are we making these orbitals. So as in case of ethene, the first and the most stable molecular orbital will have all the shaded region on the same side. The second most stable molecular orbital will have two shaded regions on the lower side, and then two shaded regions on the upper side. And the third most stable molecular orbital will have one shaded region on the lower side, two on upper side, and then again on the lower side. The most unstable will have all the shaded regions alternate to each other. And if we see, there are 4 pi electrons, so those electrons will be filled in first two molecular orbitals. These two molecular orbitals, 1 and 2, they are bonding orbitals, and the other two are anti-bonding orbitals. They are empty. Anti-bonding orbitals will remain empty. Bonding orbitals are filled with electrons. Let's take an example of 1,3,5 hexadiene. In this case, there are how many pi electrons? There are 6 pi electrons. And this is how we'll be making the molecular orbitals. So the most stable, all the shaded regions on the same side. The most unstable, all the shaded regions will be opposite to each other. So the second stable molecular orbital will have half the atomic orbital will be having shaded region on same side, the other half will be having the other side. So in the third most stable molecular orbital, two will be on same side, two will be on other side, and then two will be on same side. So on you will be having the molecular orbitals. So we have to fill 6 electrons, 6 pi electrons. So 2 will come here, 2 will come here, and other 2 will come here. Now there's a concept called HOMO and LUMO, and this concept is used in electrocyclic reactions. We'll see the examples where we'll be using these concepts. HOMO is highest occupied molecular orbital. Highest means highest energy. So this is the highest energy molecular orbital. This one is the lowest energy molecular orbital. But he's also saying highest but occupied also. But this is not occupied. This is also not occupied. Not occupied. So highest and occupied is this molecular orbital. So if someone asks you about HOMO, it should be occupied and should have highest energy. So in this case, there's only one occupied orbital. This will be HOMO. In this case, there are two occupied, but the highest energy is this. So this is the HOMO. Okay. Now LUMO is lowest unoccupied molecular orbital. So this is the second important terminology, LUMO. LUMO is lowest unoccupied molecular orbital. There are three unoccupied molecular orbitals here. Which one is lowest? This one is having the lowest energy. So this one will be LUMO. In this case, there's only one unoccupied. In this case, the third one will be LUMO. Now we'll discuss about molecular orbitals of allylic system. And allylic system is a 3-carbon system with one double bond, either with a positive charge radical or an anion having a negative charge. So 3-carbon system, there will be 3 molecular orbitals bonding where all shaded regions are on same side, anti-bonding the alternate shaded regions, and there's another non-bonding orbital which is having intermediate energy. So in case of anion, you've got 4 electrons which will be filled like this, and this one will be the HOMO in case of anion. In case of radical, it will look something like this. In case of cation, there will be only 2 electrons, so it will look something like this. So HOMO in case of anion will be this one. HOMO in case of radical will also be this one. HOMO in case of cation will be this one. N is for non-bonding orbital. So if you can observe, the bond is not completed for the terminal carbon, so there is a non-bonding molecular orbital existing in for allylic system. So the classical example of cyclization of 1,3-butadiene into cyclobutene in presence of heat. So this bond moves to this position, this pi bond breaks and forms a sigma bond, and you get a cyclic butene. Now let's see how the orbitals overlap to form this sigma bond. Now whenever we are talking about the formation of a new bond, we will be considering HOMO orbital, highest occupied molecular orbital for this reactant, which is 1,3-butadiene. And we know HOMO of 1,3-butadiene, remember HOMO contains electrons. HOMO contains electrons of highest energy, which actually participate to form a new bond. So HOMO of 1,3-butadiene looks something like this. And I would say focus on the first and fourth carbon, which we'll be using because we are considering we are focusing on this particular bond formation, the bond between 1 and 4, the new sigma bond formed between 1 and 4. And if you see the first and fourth carbon, the first carbon is having shaded region on lower direction and the fourth carbon on the upper direction. And if the bond has to be formed, these orbitals will rotate in such a way that both the shaded regions, they come close to each other. Remember, there's an electron shaded region means an electron, probability of an electron present in that particular region. So if electrons comes close to each other, a bond will be formed. So for this bond formation, the orbital will be rotated. If you see, this rotation is an anti-clockwise rotation. And this rotation is also anti-clockwise rotation. So for bond formation, we will rotate both the orbitals. So both orbitals will be rotating in anti-clockwise direction. If the direction of both the orbitals is same, be it clockwise or anti-clockwise, we call this type of rotation as, we use this term which is con rotation. Con rotation means if the rotation of both the orbitals is same. Now there's another interesting example which is electrocyclic reaction in presence of light, in presence of H nu. The product formed is same, but the reaction is, the mechanism is slightly different. Now whenever you provide some energy in the form of H nu to the orbitals, so in this particular example, now let us discuss another interesting case where this reaction occurs in presence of H nu. You give some energy and this reaction is completed. Now conversion of 1,3-butadiene in presence of H nu, which we call as photochemical reaction. Photochemical reaction. The product formed is same, but the mechanism is slightly different. Now what happens in this case is when you give H nu, which is energy, the homo electrons, they moves, these electrons move to the upper level. The upper level was LUMO. Now as a result, this becomes a new HOMO. I'll repeat again. Whenever you do a reaction in presence of H nu, so energy is absorbed by HOMO electrons and they move to the upper orbital, and by definition HOMO is highest occupied molecular orbital. Now if electrons are present here and if they are occupied, if this molecular orbital is occupied, so this becomes a new HOMO. So LUMO, the original LUMO becomes a new HOMO. So in this case you will use these orbitals for the mechanism of cyclization. And in this LUMO or new HOMO, you can see that the orbitals, they are oriented in this particular way. Both the shaded regions are on same side. Now if both the shaded regions are on same side, if you form a bond, you need to rotate it in this direction, and for this one in this direction. This is anti-clockwise direction. For this it is clockwise direction. So this means the rotation of two orbitals, two atomic orbitals, to form a new bond is not same. So for one it is anti-clockwise, for the other it is clockwise. So we use a special term in this case. In this case we call it as disrotation. In the previous case, when both the rotations were same, anti-clockwise, or be it clockwise, it is known as con rotation. But in this case it is known as disrotation. Now to summarize what we just discussed, whenever we have a 4n pi system, so a system which contains 4 pi electrons, the example that we took was 1,3-butadiene. So it can be, n can be 2, so there can be 8 pi, 12 pi. So these pi electron systems, so a system containing these many pi electrons. So whenever we do a thermal reaction, whenever we do a reaction in presence of heat, we get a product, and that product is formed by con rotation. But if we do this reaction in presence of H nu, in presence of light, then the mechanism or then the process occurs through disrotation. But what happens? Now let's see what happens if a system contains 4n plus 2 pi electrons. If a system contains 6 pi electrons, 10 pi electrons, so these systems, if they contain these many pi electrons, so in these cases the thermal reaction is followed by disrotation, and the photochemical reaction is followed by con rotation. So if I quickly give you an example of a 6 pi system, 135 hexa triene. If you see the HOMO for 1,6 135 hexatriene, you will observe that both the shaded regions were on same side, and one will be anti-clockwise, the other one will be clockwise. So one will be anti-clockwise, the other one will be clockwise. And when these are different, so we call it as disrotation. In case of photochemical, the HOMO changes. The LUMO becomes HOMO. So HOMO electrons moves to LUMO. And in case of LUMO, so LUMO in case of 135 hexatriene, if you remember, both the shaded regions were alternate. In this case, when the LUMO becomes new HOMO, so this is anticlockwise, this is also anticlockwise, so the new bond will form by Kohn rotation in photochemical for this system, 6 pi system, 4n plus 2 pi system. So if you remember, for 1,3-butadiene, there are 4 pi electrons, and 2 electrons will be filled here, 2 will be filled here. LUMO is lowest unoccupied molecular orbital. We have got 2 unoccupied molecular orbitals. The lowest one is this. So this is LUMO. How many pi bonds are broken and how many sigma bonds are formed in electrocyclic reactions? If you remember, so 1 pi bond is broken and 1 sigma bond is formed. So this sigma bond is formed, so this pi bond is broken and sigma bond is formed. This pi bond just rearranges to a new position. In 1357 octatetrene system, this system will undergo electrocyclic reaction by which particular condition? So which condition is right for this particular system? If you observe, 1357 octatetrene system is a type of 4n pi system, and 4n pi system undergoes Kohn rotation with thermal conditions. So this one is the right answer.